and welcome. I'm always so happy to see when people come to class day after a term test. I appreciate you all being here this morning. Thanks for coming last night to write that test. I think it's really, really important to have these in-person tests. I think it's it's a good thing. I did post this morning my solutions and as well as a video showing sort of what I did. I'm worried about feedback from that thingy. I feel like I'm just a little loud, I don't know. So you can check that out. I'm not going to go over the test in class because you can just look at the video and look at the solutions I wrote out. Please have patience with us as we mark this. So since there was a written problem, there will be an actual person reading what you've written there and trying to follow your reasoning to award partial credit and stuff to give you those 8 points. So that's going to take that person a little time. My goal is that we should have the marks posted by October the 19th. So I'm kind of interested to hear from you what you think. I guess the same two questions I asked for the mini test maybe is what did you think about the difficulty level, and then what did you think about the time that you had? Let me just give you 60 seconds to kind of grab your phone, see what you say here. What'd you think? So you're starting to get used to what physics tests look like? Expectations, or did I surprise you once again last night? Okay. The survey says so yeah, a little bit more towards the middle. 43% of you kind of are coming to expect this kind of stuff. So it's more towards the middle than if you look at the mini term test, which was there. If you look at, so the next question, though, is what did you think about the amount of time? Basically being like, so you had 80 minutes. Did you run out of time? So either, yes, you really ran out of time. You needed a lot more than 80 minutes to do those questions. Or you just about ran out of time, or no, you had enough time kind of thing. Maybe I'll just give you around 30 seconds to. I meant to talk about that. Let's see what else. Well, so anybody have any general questions about that test, or you think the class might want to hear it? Yep. Grace, ready? Yep.
So I have a question about, I don't remember what number it was, but it was the one where it had the labeled dots, and then it fell off at a certain point. So looking at the answer, so I had version A. It said in the question that any slight differences in the acceleration would be negligible. Like it said, like assume no change in the acceleration, and then but then the answer for the sixth dot was that it was decelerating. But in the question, indicated that there would have been no change. So just about that, I was wondering why it was marked that way when it said that in the question.
Yeah, there was a motion diagram question where it goes
Yeah.
along, slows down, then it kind of accelerates downwards.
Yeah.
So the idea
But
is
it
that
didn't really look like it was slowing down at the end. It was like very, very small. And so in the question, when it said assume that small changes in acceleration aren't taking place, I was just wondering why that was
well,
there.
yeah, basic idea is that if something's going in a straight line, the dots are getting closer together.
Yeah.
Then you know,
No. I understand why in motion diagrams, if it's getting closer together,
Okay.
it's moving less space in the same amount of time. But on the actual diagram on the page, it didn't look like they were really getting closer together. And then in the question, it said assume that very small changes in acceleration or like in the distance are like negligible.
Okay. Yeah, I'm not sure I totally follow your question, but so just all I can say is that, yeah, in a motion diagram, if dots are getting closer spaced together, what you want to do is compare velocity vectors to see if they're changing, where a velocity vector is going to be proportional to the distance between the dots, and I guess also not just the distance, but also the direction. So if something's changing about velocity, you want to try to subtract two vectors. Yeah, I don't have the question in front of me, so let's talk about it after class. We can look it up. See if there's see what people answered for this one in terms of time. Oop. Interesting. So once again, most people ran at a time. So that's pretty interesting. I'll make these tests shorter or something. What I'd like to see is that people have enough time to write these tests, and it looks like 40% of you did have enough time, but okay. Good to know. At least it wasn't as bad as the mini-term test. So this morning on the pre-class survey, somebody asked, what's the grading scale? So let me you may already know this because you read the calendar, but there's a calendar that contains all the rules of U of T. And so you should look it up, should definitely read it. This is the key table, which shows you how everything's all calculated. So good thing to know is that there's absolutely no difference between 85 and 100. Anything that you get, once you get 85, that's the highest mark you can possibly get at U of T. I mean, you could get a higher number, you get 86, you get 96, but there's no difference in GPA, so I call that overkill. 85 would be the most efficient 4.0 you can get. Also, good to know at U of T that anything 70 or above is what we consider good work. It's like thumbs up. You're doing good. Historically, U of T's averages have been around C, which is sort of around 65. I think that's sort of tended to drift in some courses, particularly in physics. I think a lot of departments still take this pretty seriously, math in particular. And I think it's sort of known worldwide that U of T does this, curving around a 65, and it's because that's a lot lower than US schools do. And the idea is if you get 50, you pass. If you get 49, you fail. And so that's sort of the cutoff mark there. 50 or above means that you're done this course, you don't have to take it again. 49 or below means you didn't complete the course. And so, but you got to be a little careful with getting C's and D's, is that if you get straight D's in all your courses, you go into academic probation. You can't graduate with a 1.0 GPA. You need at least 1.5. So you need as many C's as you get D's, or a couple of B's and A's to round it all out. So these are the rules of University of Toronto. And this test last night was worth 17% of your mark in the course of Physics 131. That's how it gets weighted. So we don't have practicals this week, right? That's correct. You don't have practicals this week. I don't like to get things all messed up with Thanksgiving, and that's the idea. So certainly Monday was a holiday, so the rest of you get the holiday as well. But next week, we're coming in with all this Chapter 5 circular motion stuff. We're going to be swinging around the rubber ball on a straw. We're also got a flying pig, which literally is a flying pig. Well, it's a toy with little wings on it. Flies around in a horizontal circle. Pretty fun. Okay. Chelsea's birthday. Okay. So how are we doing? Everyone's okay? More general kinds of questions? Like I say, if there's a mistake in a problem, I can always try to fix that, but let me know. Yep. Ready? Question. Oh, sorry. Terrible throw.
Oh,
Thank you.
Wait, is this? I just wanted to ask, like, if we left anything in the test room, like after we left, is there a way we can get it back or no?
Yeah, for sure. Yeah, there's a lost and found, either April Seeley, so room 129 is a lost and found, and also 128, MP 128, MP 129. Those are the two sort of. Anytime you leave something in practicals room or in the exam, it'll go back there. We got a couple of water bottles from last night. Okay, so this is a Google Maps image of the intersection of Highway 427 and 401. And the idea is that if you are turning, then you can specify something called the radius of curvature. So what does that mean? Well, what it means, like if you're on, I guess, the little ramp there that goes on or off, you can see it definitely kind of looks like a circle. And you can imagine the radius of that circle as being this distance right here, 75 meters. But anytime you're turning at all, I guess what you can do is kind of, for some portion of the road, you can fit or try to match that curvature with a circle. So you may not be on that circle like over here or over here, but for this part of the motion, you are on a curved path whose radius of curvature is 410 meters at that point. And it's not as curvy as the 75 meters. So, and you could even imagine over here, it's curving just a little bit. And so in this region, right from here to here, radius of curvature would be 730 meters. So any time in physics that you're on a curved path, someone's always going to tell you or specify to you what the radius of the curvature is based on. If it was a circular path for that little segment of the road you're on, what would the radius of that circle be? Okay, and I wanted to do this unbanked curve question. So this one actually is for points. So hopefully you have it. Okay, so, and once again, what we do a lot in Chapter 5 is it's a little bit three-dimensional, but I can only draw in 2 dimensions. So what I do is I draw 2 diagrams. So this is the same car viewed twice. One is the bird's eye view as viewed from above, and then right below it, we do a different view of the same car as viewed from the side. That makes sense? So there's a horizontal force which acts on the car to keep it on the curved path. Here's a list of 4 forces that we deal with a lot in this course: gravity, normal, kinetic friction, static friction. I'm telling you that one of these 4 forces is the main force that's responsible for keeping the car on the curved path. So think about that. Pair up, share with your neighbor. Give a minute to click in. So part of the whole idea with circular motion, and you can sort of see that with this string on the ball, is that there's a force which pulls inward to keep it on the path. And I think actually next week that I'm going to get a bowling ball for your practicals room and get you guys to bowl, same as Bowen did last time. But somebody should grab the hammer and try to hit the bowling ball to keep it in a curved path. And you really do find that you need a force that goes towards the center of circular motion. So let's see what people said here. Yeah, static friction is one that I like, D. So I've drawn there's a sum of forces which is going towards the center. So, and it's also on here. She always writes it as this sigma F, which is correct. It's sometimes called the net force. The sum of all the forces acting on an object going on a circular path at uniform speed has to be towards the center of circular motion. So these are not, gravity and normal, unfortunately, are not toward the center of this horizontal circle. They're up and down. So neither of those are candidates. Kinetic friction, that's not possible because the car is not, I guess, skidding or sliding. So it can't be kinetic friction. And so the only thing left is just static friction. And the reason it's static friction is because it's rolling without slipping. So even though the car is moving, the parts of the car that are actually in contact with the ground are not moving. It's the flat bottoms of the wheels. So it's a property of rolling without slipping is you've got to use mu sub s as the maximum static friction force. Okay, so you've got this force. Some people call it a radial kind of force. It's giving you this acceleration. So an object's acceleration can be decomposed into components parallel to and perpendicular to the velocity. So what you do is you actually set the t direction to be in the direction of the velocity. So this is like the path. I'll draw in blue. Then what you can do at some point, maybe here, is, I think she uses green usually to draw the velocity vector. Use green. Green. This is v, the velocity, and it's tangent to the path. So this is tangent to the curved path. So kind of by definition, velocity is tangent. But the acceleration does not have to be tangent. It can be off at some diagonal, so I'm going to draw that as A. So what you can do, though, is you can take A and you can decompose it into two perpendicular components. And we call that A sub R and A sub T. So what we've done here is we've defined this T direction to be in the direction of the velocity, and then R to be where it's turning. Okay, so A sub T is the component of the acceleration that's in the tangent direction, so it's going to either speed the object up, in this case, or I guess if it was negative in the negative T direction, it'd slow it down. And then A sub R is the component of the acceleration that causes this thing to change its direction. Okay, it's radial. And so it's perpendicular to the velocity. So an object changing direction always has a component of the acceleration perpendicular to the direction of motion. So we call that in the plus or minus r direct. I guess it must be in the plus r direction, actually. Sorry. I think by definition, the center of the circular motion is going to be in the plus r direction. So you've set up the t and the r axis. T is parallel to the velocity, and then the instantaneous velocity, I guess, and r is in the direction it's turning. So the A sub r will be in that motion. So uniform circular motion, I just want to go over that a little bit. I talked a little bit about this in the pre-class video. Is something that's going around a circular path of radius r. We would say here that T is the circumference divided by the period. And the circumference is 2 times pi times r, and period is t, vt. This is like tangential speed. It's just the speed. Equals just the speed v. Okay? And t here is the period in seconds. It's time to go around for a full circle. Time to go around full circle. So a uniform circular motion, that's what you're going to be trying to set up with the flying pig, is where the amount of time to do a full circle doesn't change, keeps going around same amount of period each time. And then if you look at the velocity, even though the speed is constant, the direction's always turning, right? So since velocity is a vector, which includes magnitude and direction, the velocity is constantly changing. And that looks like this. You've got all these green vectors. I guess if you look at different points in the motion diagram, from here to here, the velocity changes. So if you look at Vn, it's up and to the left. If you look at Vn plus 1, just one kind of step later, it's down and to the left. So still to the left, so there hasn't been much change in the horizontal direction, but it's turned. And so the change, delta V, is actually downwards for this point right here. And since delta V is in the same direction as A, it's exactly the question you were asking about from the test last night, as A, then that means the acceleration here is, for that top point, is in the downward direction. And that's going to be true of any point. If you subtract the vector just after and the vector just before, you end up with a delta that's towards the center. Remember, initial vector plus the delta gives you the final. So it's probably good practice to set up that vector addition for yourself. Make sure you believe me. And that's exactly why the force is towards the center. The force gives the acceleration, F equals ma, right, from Newton's second law. So then whatever net force, it's going to be the mass times this acceleration, which is towards the center. That's why you have to keep hitting the hammer towards the center of circular motion. So, and I would just say that this acceleration has no tangential component, because it's not speeding up or slowing down. It's uniform circular motion, so object is not speeding up or slowing down. It's just turning. So there's an equation. Let me try to step through some of what the book goes through in terms of figuring out the equation for radial acceleration. So the first thing it tries to ask you to do is imagine that you change the speed. So you've got an object at some speed, and it's turning, and you'll get a delta V. If you double the speed, then what will happen is, if you take those same two points on the circular path, there will now be half as much time. So if you're going to find acceleration, which is your delta V, so delta V will be twice as much. And then the delta T will be half as much. So so if you want to find acceleration, which is delta V over time, delta T, then since your velocity vectors now are twice as long, when you subtract them, you get delta V is 2 times delta V. Also, since your time is half as much, you'll have a T over 2 on the bottom. You end up with a 4 on the top. And if you were to do this with 3 times the velocity, you'd have delta V would be 3 times greater. Also, the time would be a third, right? So 3 divided by a third is 9. So the argument here is that the acceleration has to be proportional to the speed squared, as long as the radius is fixed. So hopefully you followed along that. They're trying to derive this v squared over r thing straight out of your textbook. The next step she does is imagine that you don't change the speed, you just change the radius. So here's a sort of a small circle, some r. There's an initial and a final. You take a delta v, and there's some time. What if you then choose the same speed, but make the circle twice as big? Well then, what you have, if you're going to choose the same, I guess, angle or something, then that the v at the beginning and the v at the end will be the same. They're just farther away from the circle, the center of the circle. So delta v here is the same. What's changed now is that now it's twice as far. So that means that the time will be twice as much. So delta v is the same. Delta t is now twice as much because it's twice as far. So now the acceleration, delta v over t, is half. It sort of makes sense, right? If you're going some speed on a road and it's a really tight curve, r is really small, you're really going to have to accelerate a lot to stay on that curve. Whereas if it's a much shallower curve, like those big radius curves on the highway, then it's less acceleration for the same speed. This is why it tells you to slow down on off-ramps, for example. So conclusion here is that the acceleration for a fixed speed is proportional to 1 over r. And you combine those and you get v squared over r. And the units work out nicely as well because you've got meters per second squared, so it's meters squared per second squared, and you divide it by meters, and you end up with meters per second squared. So that's your equation. You were asked about that on the pre-class quiz, weren't you? If an object is moving with uniform circular motion at a constant speed v and radius r, then its tangential acceleration is 0. So a sub t is equal to 0 because it's not speeding up or slowing down. Then the radial acceleration is v squared over r. Got that from your reading. Do you want to try a bit of a tricky top hat one? You got a car that's traveling east, but it's turning. And the speedometer is sitting at a steady 100 kilometers per hour. So the car is neither speeding up nor slowing down. So what's the direction of the acceleration at this instant? Is it A is it north, B is east, C it's some diagonal between east and north, or D it's some diagonal between west and north, or E would be that the acceleration is 0. So there's no direction to 0. Give you a couple minutes to talk about that. So think about it, and then pair up and share with your neighbor, please. Okay. Survey says, some people are saying here. I think the lights are a bit better. Thanks for that. North, yeah, that's what I like. Maybe not that tricky. But basic idea is that someone was asking, are you turning? So when I was a kid, I always thought that driving was like you're doing this all the time. But if you actually start driving as a grown-up, you realize you do like this. You're not actually turning the wheel all the time, or else you'd be going all over the place like this. But so what's happening right now is that I'm turning, meaning that the steering wheel is not straight, it's turned. And it's just actually fixed like that. And also, your speed is fixed. So it's a weird situation. But you have to be accelerating. And there's no component of your acceleration in the east direction, otherwise you'd be speeding up. There's no component of your acceleration in the west direction, or you'd be slowing down. The fact that you're at a steady 100 kilometers per hour proves that the acceleration must be perpendicular to your instantaneous velocity. It's got to be north or south, or else you'd be speeding up or slowing down. And then it's north because the center of the circular path is in the north direction. It's the radial direction. Okay. And we had some, so yeah, north looks like that. There's acceleration, there's velocity. Whoop. And then I just want to talk a little bit about uniform circular motion, to just say that if you've got some vt, I guess tangential, and there's some r, then the acceleration in the t direction is 0, and the acceleration in the r direction is v squared over r, or I guess this would be vt squared over r. Same thing. But we talked about, I guess, a merry-go-round in the pre-class quiz this morning. So what that is an object that has some fixed rotation period, t. And so if you're at some distance r from the center, then you're going to go around in some circular path at some speed vt. And so vt is 2 pi r over the period, where 2 pi over t is a constant. So what that means is that as the r increases, if you're on a merry-go-round, one of those rotating platforms at the playground, as you go closer and closer to the edge, you're actually speeding up. You would not be moving at all if r equals 0, right? You'd just be kind of spinning. But as you get towards the edge, you're going faster and faster and faster. And the kids at the playground, sometimes they link up their elbows like this into a big line and try to go around in a circle. And the kid at the very end is going, ah, flying out because they're going so fast. And that is because of this equation. V equals 2 pi over t. T is a fixed number. And r increases away from the center. And you can work it out for radial acceleration as well. Remember, radial acceleration is vt squared over r. So what you can do is plug in, it's 1 over r times 2 pi r over t squared. And if you distribute this squared in here, you get 1 over r times 4 times pi squared, there's an r squared, and then you divide it by t squared. So the r squared on the top cancels one of the r's on the bottom, and what you get is that it's equal to, it's equal to a constant of 4 pi squared over t squared times r. This is a constant. Okay? So what that means is that for a merry-go-round, as you get further from the center, your radial acceleration gets bigger and bigger. And that's why it's harder and harder to hold on for a fixed period. Is that making sense? It's a matter of trying to, because I know it's v squared over r, right? And so you'd think that the radial acceleration would get less with increasing r. But your tangential speed gets bigger as r. And so there's an r on the top as well, r squared on the top. And that's what was going on with these questions. Girl and boy are riding on a merry-go-round. The girl is near the outer edge, and the boy is closer to the center. Well, the tangential acceleration for uniform circular motion, because of this constant rate thing, is 0. At equals 0. So that doesn't matter. Not speeding up or slowing down. But the radial acceleration, I would just say, I would have to use 4 pi squared over t squared times r, I guess, right? The girl is up towards the outer edge, so she's got a greater radial acceleration. It's a bit of a tricky one. I had some little survey, some interesting things. Acceleration breaks down into its tangential acceleration and radial acceleration, but velocity is only tangential. So why is there no radial, I guess, velocity? And so what I would say here is that tangential direction is by definition the direction of the velocity. So that radial component of the velocity is 0 by definition. I wonder if you could explain why the centripetal force results in constant velocity, even though there's an imbalance of forces. So it's actually not constant velocity, it's constant speed. So the radial force is what turns the object. Since velocity is a vector, which includes both magnitude and direction, if either one of those change, you need an acceleration in meters per second squared. That's where that's coming from. Okay. So it is possible, if there's no tangential component to the force, for the speed to be constant. All right. What else we got here? What happens when in circular motion v is not constant? So that's a great question. It's fully possible for circular motion to be speeding up or slowing down. What you'd have then is you'd have the radial component would still be v squared over r, but now you'd have an additional tangential component to the acceleration. So the acceleration would be on some diagonal, where you use Pythagoras and you do a r squared plus a t squared and the square root of that. It's not too hard. And then the v would be changing with time. So I guess your v squared over r would be changing with time, so the acceleration would change with time, but that's okay. Want to do another top hat? Okay. And this is, we're going to do this in practicals next week. Like I say, there's going to be at least 3 fun experiments next week. One is flying pig, one is whirling a ball in a vertical circle without hitting anybody, and the other is the bowling ball. But as far as this one, where am I going here? At what point is the tension going to be greatest on this vertical circular motion? When it's greatest at the top of the motion, B, it's just constant, C, greatest at the bottom of the motion, or somewhere between the top and the bottom. Yes. Try to think about that. Whoa. Didn't give it enough. Think about it. Pair up and share with your neighbor, please. Make sure you're voting the same way as your friend. And if you're up in the balconies, I would encourage you to get a neighbor. Just yell to each other. A big part of university life, I think, is making friends. Surfaces C, which is also what I liked, the tension is greatest at the bottom. So my explanation for that looks a little like this, and we can do an actual example. But as the ball goes around in the circle, it must be accelerating towards the center. We know that. And so you need the sum of all the forces, the net force, to be towards the center of circular motion, or at least to have a component that way. And what are the forces on the force diagram for this ball? Well, it's the tension and gravity. Those are the only 2 forces, I think, acting on it. And I guess maybe a small amount of air resistance, but which I guess we could neglect. But anyway, at the bottom of the motion, your force diagram is gravity acting downwards and tension acting upwards. So gravity acts in the wrong direction. It's away from the center of circular motion, so you need a greater tension down there to compensate. And then also, I guess it's probably moving faster down there as well. It's probably not uniform circular motion. Probably speeds up on the way down, which even compounds it even more. So, and we can do an actual example. A 0.3 kilogram ball is whirled on a string in a vertical circle of radius 0.8 meters. So let's do a diagram. Here's r is equal to 0.8 meters. And at the bottom here, it's moving at v is equal to 3 meters per second. What is its acceleration at that moment? Well, it's pretty easy, I guess. Acceleration at that moment, a sub r, so we define at this moment, r is up and t is to the right. Those are our axes. Instead of doing x and y, I like to use r and t for circular motion. T being tangent to the velocity, r being towards the center of the circular path. So it's just equal to v squared over r. So it's 3 squared divided by 0.8, and I get 11.25 meters per second squared. Okay, so, and that is in the up direction, plus r direction. It also asks, sketch a force diagram for the ball at that moment. Well, you've just got the tension of the string, I guess, on the ball, and you've got the force of the earth on the ball, which is the mass times g, right? And then the acceleration, I like to draw it here beside the force diagram, showing which way it's accelerating up. And C is what is the tension in the string at that moment. That's sort of what the quiz was about, right? So you can now say that, well, the sum of all the forces in the r direction is equal to m times the acceleration in the r direction. So that's equal to m times v squared over r. So what are the sum of all the forces in the r direction? Well, you've got T minus mg equals mv squared over r. So that's what the equation looks like at the bottom. And you're supposed to solve for T, so you can just do T is equal to mv squared over r plus mg. And you can say it's going to be 0.3 times the 11.25, I guess, plus 0.3 times 9.8. I think I got 6.3 newtons, which would be a lot more than the 3 newtons if it was just hanging steady. To keep it in a circular path, you need to have more tension on it. And you can kind of see, even when I swing it in this, and you'll feel it, I guess, when you do this in lab next week, is if it goes too slow, the tension almost goes to 0 at the top. It can actually, it's no longer taut, right? I remember as a kid, I was on this playground on swings, and I always wanted to go all the way around. But I always got the bumps before that happened. Has that ever happened to you? You get the bumps, right? And what that means is that the tension is no longer, it goes less than 0, and then you turn into a projectile, and then, so you can never go all the way around. It's always a big disappointment to me. Okay. So, all right, so the next thing is I'm going to take a coffee cup and swing it over my head, and maybe the coffee won't fall out. So I'm going to do that right in front of your laptop, if that's okay. This is getting a little empty, so let's fill it up. So I got a nice full cup of water. Fill it right up. I'm going to take this CD case on a string, and then I'm going to just, oh, it looks a little tippy, doesn't it? Getting a little tangled. That should be okay. Put the cup on the tray. Right. How's that look? Swing it around in a circle above my head. So why didn't the water spill it? Want to see me do it one more time? Should we tempt fate? It looks a little tippy right there. I definitely need to untangle this a little. Let's do it one more time. Right around my head. Okay. So now you know a party trick. Half of physics is party tricks. Okay. What time is it? Yeah, we got 3 minutes, so let's just go through it. So if your car turns a corner, you feel thrown against the door. Now, I also remember this as a kid. It was me and my sister in the back seat, and when they would turn, we would get squished. So back in the old days, they had bucket seats, and we would end up squishing into each other. So anyway, you do kind of feel like you're getting pulled towards the edge of the car, the outer edge, which is a bit weird. Because I'm telling you that the actual force on the car, and even on you, is towards the center of the circular path. But I guess in your accelerated frame, your non-inertial reference frame, you feel pulled to the outside because what you want to do is go on a constant velocity in a straight line, which will kind of take you towards the outside of the car. So you try to keep moving straight ahead, and what happens is that the edge of the car gives a normal force which pushes you towards the center of the circular motion. So in your accelerating frame, you kind of feel like you're being pulled to the edge. And that's called the centrifugal force, and that's exactly what causes all the little platelets to fall to the bottom of the centrifuge in the test tube when you spin it around, is this fictitious force. But in the inertial frame of the ground, the only real force is towards the center, not away. It still works to separate blood. So, the minimum speed of the water at the top of the vertical path is that at which gravity alone is sufficient to cause circular motion at the top. So, and that's called V min is square root G over R, G times R. So, if I'm going fast enough, if I keep that thing and it's spinning at a speed that's greater than this square root g times r, then what's required is not just gravity, but a normal force from above pushing down to keep that water going on a circular path. So that's the whole trick with this party trick, is you got to really spin it up so that you need extra force from the bottom of the cup to keep the water from going in a constant velocity, a straight line. In order to stay in the cup, it has to get pushed inward towards the center of circular motion. If I don't do it fast enough, then, so there's a minimum speed. If I don't do it fast enough, if I go slower than that, then what will happen is that gravity will pull the water out and it'll splash all over my head. That's when the normal force goes to zero, because the normal force always has to be away from the surface. All right. Somebody asked on the pre-class survey this morning, what's going on? Considering the Earth's radius is 6,400 kilometers, and the astronauts in space stations are only about 500 kilometers up, then why are they weightless? Because there's all these videos on YouTube of them like floating around and drinking like balls of water. So that's what we're going to take up on Friday, is why do the astronauts feel like they're weightless? All right, see you Friday.